position, more complex geometry we have, the difficult it is to actually run. All right. Then after that, you have after your geometry operation, now comes material. Material selection now becomes one of those most important, like one of them, but still the most important part of simulation, because in fact material tells you how. For instance, let me give you a quick example. This model itself, you can't tell the mass of this model, right? If you're calculating for mass physically, you need the density of that particular object. You can't calculate for mass if you don't have the density, and density only comes with material. So you have to know the density, meaning you have to know the material before you can actually calculate for the mass. So at the end of the day, this right here is just an object. Like if I go check my evaluate, I go check my mass properties, 5.53 grams. In fact, it might as well be zero, right? Because it's that 5.5, it's just, let's say it's just a placeholder based on shape, rough based on shape and size. It's not taking in any material density into account. You understand? It's just pure geometry. It's not taking material into account. Okay. Now, okay, yes. Now, materials. You add materials to this, and immediately you add a material to it, you get you now get a geometry. For instance, whatever the length, let's take an example. If we're measuring, let's say we're measuring here to here, and let's say this line is, let's just measure this line is 105 millimeter, approximately 105 millimeter. It's just 105 millimeter. It's nothing, right? It doesn't make any sense. It doesn't represent anything. Okay. So if I go material, edit material, and then I add okay, let's say alloy steel. Alloy steel has a mass density of 7,700. Okay. Okay, most importantly, has a yield strength of 620. Okay, apply my material, my alloy steel, and then all of a sudden this actually becomes a shelf bracket properly. Okay, if I go for my mass properties, you can look at it and see, okay, it now has a mass of 42.5. Now you can see explicitly this is 42.5. Now there's no disputing the fact that this is what it actually is in terms of mass. Okay. Okay, now a warning first. I give every single class, I everyone I give a single class I teach, FEA does not make you like, it doesn't make you like right per se. It just makes you a bit precise. Okay. And being precise and being correct are two different things. Okay. The steps I'm going through, if you run a simulation without picking material, and then you get a solution, it's going to be a precise solution, but it wouldn't be a correct position, a correct like a correct result. Okay. So precision and correction are totally different things. And if you set up your simulation wrong, let's say you pick the wrong material, or when it comes to the fixtures, or when it comes to the meshing, SolidWorks is going to give you very, very perfect, beautiful stress bar. It's going to give you every single thing you actually want, but it's not, because it trusts that every single input you are putting, that's what where the engineer you are comes in. It trusts that every single input you're putting is information that it actually needs, that you actually need. So it doesn't take into account things like that you might probably make any single mistake. Okay. So yeah, we've added material, right? So after you selected your material, the next thing now is for you to actually start running the simulation. So if you don't have simulation laying out for you, on these tabs, select tabs, and turn on simulation. It should be okay. or basically just search simulation. Let me see. Okay, yes, and simulation is split into two: simulation expert and simulation expert, analysis wizard, and simulation. Both do the same thing. We a couple of months ago, I had a situation where we were trying to run a simulation and someone got different answers than I did, and we later discovered she was using experience expert, SolidWorks simulation expert. So we kind of like checked the both of them and found out that the reasons why they were be giving us separate answer, but everybody thought it was going to be like a bit different because of it's. But at the end of the day, we came to a one answer because the person's meshing was a bit different. Okay, what simulation expert actually basically is it just basically it's kind of like a tab that guides you on what to do, what next to put, what next not to put. That kind of like the simulation process I'm explaining for you, but it comes out in text. Okay, so first things first, you pick a new study. Uh, we're working with static study. You can name it, let's say, shelf bracket. Okay, shelf bracket, and then you click your this thing. Okay, all right. Now, first things first, they let you know is your material has been checked. Now, um, every material has a limit. Okay, every material has a stress level beyond which it actually stops being elastic. So meaning it stops returning to its original shape, and then when you remove the load, it starts to permanently deform. Okay, and that's called a yield strength. Okay, beyond that yield strength, the material or the part or the bracket or whatever we're working on becomes damaged, and even if it doesn't look broken, SolidWorks doesn't show you deformity per se, but with the value you know that it is broken. So how do you know, right? How do you know, okay, this material has failed, this object has failed? You have to know the material you're using. Like I said, when I was applying alloy steel, I told you that I specifically said, okay, this is the yield strength, it's about 620, I think. You know that it's 620. You understand? So you can see that it's 620, you know it's 620, you just know. So when your yield strength exceeds that, you can what's it called? You can just basically know, okay, simple as that, your result has failed or your material has failed. Okay. Now this is what I want you to also understand. Not like you kind of like cramming it, just that when you apply like a force to a solid object, that the object doesn't really like kind of like sit down there. Okay, like the material is will always try to kind of like resist it by either stressing or by like compressing. You understand? So the the basically that internal resistance, depending on where you're actually applying your force, or whether you're applying it, you, you are kind of like stretching it out or you're trying to like compressing it. Right? That internal resistance, the force per unit area, is what we call stress. So stress units is basically in megapascal or pounds, but you can change it anyhow you want. But depending, it's just basically depending on the unit system you are currently working on. And then when you are applying materials, let's say I want to apply materials, right click, apply a different material. You get the option of actually changing your units, okay, to the one you actually understand. I prefer megapascal because it's a bit wholesome, right? If I go alloy steel, it tells me that I have a use strength of 620. Anything beyond 620, the material fails. All right. Okay. Now, all right. So I'm going to set. Let's. So we are setting up the mat. So we're setting up the close. Okay. So the whole idea now I'm trying to say is that when SolidWorks gives you like a stress plot, what we're basically doing is kind of like comparing the stress the part is experiencing against the material's yield strength, basically at that. So if your maximum stress is below the yield strength, your material is safe. Okay. You can now start talking about the appropriate margins, like how safe is it really? What is the factor of safety? How did it really deform? Even if it's safe, right? Didn't break. How did it actually deform? Then you start thinking about this. But on a basic level, first question is, does it fail or does it not fail? And how do you know if it fails? You compare your stress to your yield strength and compare them and see, okay, it doesn't fail or it fail. That ratio, right? Basically, that ratio, that what's it called? That yield strength divided by the actual stress you actually getting now gives you your factor of safety. You now can start talking about how well is it safe, how many use does it have, those kind of plenty things. Okay, so now let's just continue. With let's say this is a shelf bracket. Now, if you know a shelf bracket, it stays on the wall, right? And then it's supposed to kind of like stay like this, if I remember correctly. Yeah. Okay. Yes. Something like this. Okay. Something like this. So this places is basically pinned to the wall, and then you put your load or your wood, whatever it is here. Right. Simple enough. Okay. Now, yes. Now, one. I don't think both of them are equal. They are not equal. They're not equal. Yes. Both arms are not equal, so the shorter side should be the longer side should be the one holding the load itself. Okay. All right. Now we've let's just brief recap. We've added material. We've talked about geometry, how you should actually take out the necessary parts when you're doing a simulation. We've talked about what actually happens when you don't select your materials. We've talked about how we actually calculate the stress if you're using hand calculation and all that. Now we've entered the simulation itself. Now we've added materials. Next thing is to add, we know you're working with connections, because connections only come in when you're working with multiple parts like assembly. Okay, we'll skip connections. Now let's talk fixtures. All right. Now, fixtures is, in my opinion, when it comes to designing in general, you treat it. I don't know why I say it a lot. You treat it like it's actually happening in real life. Like, this is how it would go if you were working in real life. For instance, sorry, Timothy, please, can you hear me?
Yes, sir.
Yeah, how many minutes do I have, please?
So we have from 8 to 9:30.
Okay, all right, we have time. Okay, sure. Okay, now, all right, okay, as okay, let's continue. Okay, now fixtures basically define they just physically come on, it's simple enough. Physically, where you are actually constraining your design to, where are you putting it? Are you nailing it? Are you using gum? Are you kind of like gum hit leaving it there, holding it with magic? However it is you decide to hold it on the air, it's called a fixture. All right. So sometimes people get it wrong because of how, well, either what kind of fixtures are you working on? You're nailing something and you're going with and you're using a fixture that mimics when you're basically gluing the thing, or when you're just sticking it there with some superpower. So the whole idea for you is to actually pick your fixture. What are you nailing with? Are you nailing? Are you gumming? Are you whatever it is you're doing? I just only know nail and gum because the model I'm looking at right now, you're either gluing the thing to the wall or you're either nailing it to the wall. Okay. So I'm going to go fixtures. I'm going to right click on fixtures. They have a whole lot of types of fixtures depending on what you want. Fixture advisor just tells you what kind of fixture it feels, it thinks. But your engineers, you don't need someone to tell you what you're doing. You've seen the physical product, you know it goes to the wall. So we're using a fixed geometry. Now the question now comes selecting where it's actually been fixed. So like I said, this is going to a wall. So, and if it's going to be nailed, so I'm assuming the fixtures are going to be here. Let's see here. It's going to be here, and then it's going to be here. The beauty of this is that the process itself sorry, the process itself doesn't really vary from normal from different, like it doesn't vary from when you're working with different designs. It's almost almost always the same. There's no much process to the whole thing. Okay, so even if you're doing a different design with working with a different model, the whole process is kind of the same. Your geometry, you get your material right, select your material, you get your material right, and then now we're in fixtures. Okay, so easy. You go through and look at it and see, okay, it's properly fixed. You can turn it, rotate however you want to make sure that it's visible. Should Now the question is this: your direction is automatically fixed. Like your direction, when you like, is it going to be, the fixtures, are they going to be fixed to this side, or are they going to be fixed to this side? It's just trying to basically restrict every single degrees of freedom it actually has, right? Ordinarily, the plot isn't floating in SolidWorks, but it's assuming that it's not fixed. If you run a simulation without it being fixed, yeah, especially if you're doing SolidWorks assembly, if you're doing assembly, simulation assembly, and you maybe the connection between two parts are wrong, it's going to fall, it's going to move infinite times. So it's going to give you an error and tell you that it's sensing a very, very large deformation that's unrealistic. Sometimes you use the word unrealistic, okay? So in real life, only the three screws constrain in this actual part. Only three screws constrain it. The rest of the back face isn't, they're not glued to the wall. Okay, so that's the reason why we are not adding we're not selecting the faces also. Okay, they are not glued to the wall. All right, and so fixing the three bolts is more realistically than you kind of like selecting the part, because you won't get an accurate result. However, the nuance now is that this fixed geometry on the whole assumes that the screw is infinitely rigid. Okay, so and basically what it means is it doesn't allow any space for like rotation or deformation at that hole, which is not really 100% realistic. Okay, but for today we are learning fundamentals, and so we accept that simplification on an ideal state. So when you're working, well, if you're working for like advanced, when you're doing advanced simulation, you'd want to use pin, right? Pin connection instead of like just fixed. Pin connection is a bit ah, like it's fun, right? It's fun. I use it only when I am kind of like connecting two parts. I'm two part, like I have two parts, and obviously I know they won't be realistically fixed to that part, right? So I would just want to use what's it called? Use pins. Okay. So now, once you've done that, once you've uh, selected, you've fixed your geometry, you just press OK. Now, how many steps have we done? Four or three? Three steps. We've selected, no, four. We've picked our geometry, which is this. We've selected the shelf. We've selected the material. That's two. And now we've added fixtures. That's three. Okay, good. So now let's apply load. Okay. Now I need to pick the face where the load is applied, right? Like in reuse, the wooden shelf board sits basically directly on this part, okay, and everything else pushes it kind of like straight down. Okay, so what I'm going to do is I'm going to go external fixtures. We're going to use force. You have a lot of things. You have torque, you have pressure, you have gravity, bearing load. Oh my god, there's a lot. Like if you were taking even flow effects. I've used flow effects for a simulation. We we were running CFD for a specific design, like computational fluid dynamics for a design, and it was like a billboard, right? The person was working on a billboard, okay, but they were kind of like they wanted to know the amount of force. They wanted to see how air actually kind of like passes through the billboard, how the billboard reacts to the how we react to the air passing it, certain types of if the speed of the wind increases. But not just that, they wanted to see how it would actually feel. So we had to run CFD and take the simulation results, like the simulation F1 file for the simulation, and then come to the actual now start performing a structural what's it called on simulation on the part itself, and then imported the results of the CFD into it. So it's interchangeable, and when you know what you're doing, it's very, very fun. Boring, but it's fun. Okay. Now I'm going to go internal load. I'm going to select first, and then we're going to select these phases here. Okay, good. So yeah, this what's it called? By default, it's gonna go down. So SOLIDWORK applies the force normal to a selected face, obviously. So if the face is like horizontal like this, the force is gonna go down, right? But it's still good to kind of like double check. If it's not, all you have to do is reverse it. Okay, simple, reverse and reverse. Okay, and then because you want to put it down realistically where gravity actually falls, and that's downward. Okay, so before that, you sometimes sometimes you have the opportunity to select the direction you want it to go, right? Like if you really not really sure about where the actual, like if I select my top plane. So now let me give an example. Let's do this. This is how our design actually looks compared to the front plane. Okay, so if I select the front plane itself as my direction of force, there's no way I'm going to get an accurate result. All right, I didn't model this specific part myself. I downloaded it online for this purpose. So we're going with normal. Okay, all right. Now for let's talk a bit about, okay, let's see. Right, so we've added materials, we've selected our geometry, we've added materials, we've added fixtures, we've added the force. Oh god, I didn't even give a value for the force. Give me a sec. Now I don't have I don't know the appropriate value for this force, but I'm going to, for this math, I'm going to use 15 Newton. Let's just try 15 Newton. Let's see. Okay. Or okay, let me just do this. Let me do something. What's it called? Gravity is 9.5, right? If we're using something like, if we're using 9.5, if we're using something like, let's say we're using a load. Let's use load. Let's say we're using a load of something we know. Let me imagine how load seems. Okay, let's say we're using 15 kg of load, 15 kilogram of load, and force equals mass times gravity. So 15 times 9.8, 9.81. Wait, give me a sec. Let me use my calculator. 15 multiplied by 9.81. So okay, approximately 147 Newton. Okay, so we're working with like 15 kilograms. All right. I'm typing 147. Okay, perfect. Now, let's do a quick check. Everything is appropriate. Yeah. Now, honestly, yeah, because I want you guys to think like engineers and not like software, they're just basically using the software. 147 is spread evenly across the face, right? Like across the face of this the flat surfaces. Like, you understand? But realistically, for shelf, it is not still like perfect. We know that, right? Because if you're whatever it is you're bonding it with, if you're bonding it with nails, there's no way it's going to be 100% perfect. All right. So we're just working with, okay, this is the fundamentals. All right. So because the stiffest part, the whole thing, the whole idea of SOLIDWORKS Simulation is that you always want to go towards the kind of like the stiffest part, which is kind of like the elbow part of it, because that's kind of like the strongest part of the entire design. So applying it like as we did with like uniform pressure across the full top, it feels a bit reasonable. Okay, so it's kind of like an acceptable simplification that we can, okay, go with and say, okay, we can at least get an accurate result. But if we wanted it to be much more like realistic, okay, if we wanted to more, we would model the wood board itself as separate parts and let contact connections, actually local interactions and component interaction do the work of like adding the force itself realistically. Okay, then we can now do this. So it's probably going to be two for them, and then we can now basically put this force itself on that specific part. So I'm saying this because I'm trying to not just show you how to use the software, but to understand how, sorry, he would work like realistically. All right. So good. First, next is meshing. Meshing is an amazing concept because, well, meshing. Um, sorry, give me a second. Okay, all right. Sorry, Timothy, can you hear me, please?
Yes.
All right. Okay. Sorry, I had a call. Sorry. Okay. All right. Machine. Very, very important. Machine is one of those people skip meshing because meshing is basic, right? It's either it's coarse, it's either it's fine, or it's either in the middle, wherever works. But I said earlier that FEA breaks your part into thousands of tiny elements, solves it one by one. So meshing is literally that. So it's kind of like the process of dividing your model or your physical model into continuous solid geometry, kind of like tiny particles. Sometimes, God, what's the shape called? Tetrahedral shapes. So yeah, so basically, the shapes itself, there was a time I remember the shapes itself, they vary. They vary, of course, depends on how fine you want it to be. So the depend on how fine you want something about that. But the only thing is that the only thing you have to notice is your mesh directly contributes to the accuracy of your results. That is one. So a coarse mesh would mean that your models are split into bigger components. Okay, so it's going to be like, since they are bigger components, it's going to be like fewer, and then it's going to mesh faster and it's going to solve faster. But your result is going to be a bit vague. So, or when you now use the fine meshing, it's going to be, since it's split it into smaller parts, it has much more smaller parts and much more parts to actually design, to actually like kind of like walk through. But you are going to get like a much more precise result, but you kind of like, it's going to waste a lot of time for it to actually work, so it's going to take longer. So the real skill isn't really kind of like the most finest kind of like the most finest or the most non-finest. Actually, it's kind of like knowing where and how, or basically at what point you need your mesh to be fine, at what point do you need it to be coarse, right? So for instance, you don't need it for something like this, right? We're working, you don't really need a precisely mesh. Okay, you don't need a precisely mesh design mesh, because first things first, was I know what it's called in CFD. I've forgotten what it's called in FE. What it means, if you know the name, you can type it on the chat. What it means was is this kind of like continuity, like, oh god, when you get a result, right? When you get a result, an accurate result, and then you continue, like if like, okay, let me put an example. CFD works with iterations. Like it runs it's an iterative process. It checks and checks and checks and checks. Sometimes you have up to almost 100 iterations throughout the solving process. Now, let's say you choose a very fine mesh, right? You've gotten your values. Okay, you've gotten your values. Okay, but you keep it keeps still iterating. So the difference between them is at least like less than zero point 0.5. You get, so there's no, it doesn't go up, it doesn't go down, it doesn't go up, it doesn't go down. So you first, let's say you it runs an iteration and you get a value of like zero point 0.5, and then you run again, you get zero point 0.5 and zero point 0.4. The next iteration 0.5, next iteration. So basically, it's kind of like using a whole lot of computational power for something that doesn't really need it. You understand? So it's kind of like overcompensating for something that requires would do. So basically, right click on your mesh, select create mesh. Now you can choose coarse, you can choose fine. So I would say let's leave it at the middle, all right, where it is. Um, Mesh parameters, coverage, you have the curvature based mesh and the standard mesh. Blended and curvature mesh is the one I prefer the most. um, for instance, my certified SolidWorks associate simulation exam, I failed it 3 times. Why was because the meshing, every time they asked the question was use standard mesh, and because of the write up when the question was a lot, I didn't know like this said use standard mesh. I was using blended curvature mesh, so it was always giving me answers, and these questions have like a certain error percentage and you cannot exceed them, so you failing and keep failing and keep failing, not knowing why you're failing. So that's why the little details actually matter: standard mesh, curvature based mesh, blended mesh. You understand? All right. So all right, okay, before we what we do is this: when we run this simulation, something I want you to remember, we are going to come back, we're going to refine the mesh again, and then we're going to run again and kind of like check and see how it's going to look like. You understand? To see if we actually get something different, or at least different value or a better value. Okay, so yeah, mesh control. Let me see. Mesh control are for situations where you actually, let's assume the overall purpose of this design was to actually check for this specific point. Now, mesh control basically means you select where you want, like you don't want to run a fine meshing on the entire part, which we don't need it. So you're kind of like focusing and saying that the fine meshing should be on this specific part. That's what mesh control actually does. Okay, so don't waste time computing time making the entire part ultra beautifully finely cut when it doesn't need it. All right, so okay, it's a kind of like when you need 10% of your strength to actually punch something, you're now using 60, and then it's kind of like wasting it, and then you're the longer it takes to actually run the mesh. You give it a few seconds to mesh. Now, depending on your laptop, right? Depending on your like your PC, whatever it is you're working with, it kind of plays into account how fast and how slow your simulation is going to be. Because if you've done CFD before, when you're trying to run your simulation, it kind of asks you to pick like on your laptop how many cores of your laptop's computational power do you want to use. So most laptops, basic laptops has like 4 cores. So it tells you, are you using one specific core for this, your like your processing for processing, or are you using the entire 4 of them? So if machine is taking this long, I think, all right. All right.
Mr.
Yeah,
Donald, sorry. Sorry,
yeah, I can
please.
hear
Let
you.
me just give them an attendance. Please, you can start filling your attendance form. It's on the chat. Yeah, you can go ahead, Mr. Joseph.
All right. Okay. Thank you. Yeah. In front of mesh. Okay. So I can easily say, okay. All right. Let's just run out our So run down first. Select your geometry. Remove every single unnecessary part from your geometry. Then number two, what was number two? Material selection. Select your materials. Know which materials. Know what material you're actually working with, and so you know the density, you know the use strength of the material. And then number three, fixtures. What part is going to be fixed, what part is going to not be fixed, and what kind of fixture are you working with. Number four, then you have loading. What kind of loading are you going to be using? Is it pressure, is it gravity, is it force? What kind of pressure are you going to be working with? And then number five, meshing. You mesh, choose the kind of mesh you want to work with. Are you working with a coarse mesh? Are you working with a fine mesh? Are you using mesh control? What's the purpose? Why are you doing so? Then you run your simulation. Uh, right click and run. So what the server is actually doing now is what the server is actually doing is it's kind of like running using your computational, like your machine, your laptop power, and kind of like checking and checking and checking and checking. Okay, perfect. All right. So first things first, you want to do is simple. You want to first things first you want to do when you get result is now, like I said, interpretation of the result is the most important part. Sorry, Timothy.
Yes, I can hear you.
I'll be leaving at like 9:10. I have like
Okay.
I have a commit. All right, thank you. So
Okay, that's fine.
right. So now, first thing what you have to do now is clean up your design. Okay. Now, as it is like this, there's no single. I'm not saying kind of feeling it clearly. Okay. First thing you want to do is kind of right click on your stress first, edit definition. Good. So for mean stress, you want to turn this to megapascal first. Then chart options, you want to show maximum, and then you want to show minimum, and then you want to change this from scientific to floating, and then you leave your decimal place as 3, and then you see, let's see, okay, definition, okay, all right, amazing, perfect. Now it's easier to understand now. Okay, so if I ask a question, did this material fail? Yes or no? It did. Okay. Von Mistress plot is not kind of like the real physical stress direction. Okay, it's kind of like the calculated equivalent of the stress. Okay, it combines all the stresses components. It combines your normal stress, your shear stress, and puts it into one and gives you as your for least stress. Okay, so normal, so it's not like we are kind of like separating it. It takes into account the amount of everything stress. It gives us one kind of single number that actually judges failure against it instead of kind of like taking each stress one at a time. Okay, so now notice where the stress is most concentrated. Should be here. See how red it is. Okay, so it tells you that this is where the force is actually being applied at the most. This is where failure actually occurs from the most. And now, did it actually fail? The maximum stress is way bigger than the yield strength of the material. Okay, so it tells you your material actually failed. Okay, so now this is interpreting it, like I said, is one of the most difficult parts to do because sometimes clear definitions are not given. Like, what are you doing? What are we doing? It's not given. What do you want? If your question was simply tell me where did it actually fail or not, easy enough. We've answered that it failed. Simple. How do you know it failed? Well, the stress, vomit stress, is a lot larger than the yield strength of the material, so we can tell it actually failed. Okay. That solves that. Okay. How did it fail? Like, at so at what point did it fail? You can say, okay, yeah, the stress itself was actually particularly very strong here. And then if you want to know, like, okay, let's say this is 9, right? You can probe your results. Here's your probe. Let's see. Probe. Good. You can probe and see what specific at selected entities. Let me see if I can. No. Okay. Okay. Yes, sir. All right. Give me a sec. Hmm. Okay. All right. Whatness. Right. Now, if I want to know what probe actually does, what probe was actually supposed to do, let me go back to probe. Okay. What probe is actually supposed to do, right? Probe gives you kind of like tells you you can select on any single like specific location you want, kind of like it tells you what the stress actually is on that specific like for instance you ask like this place is red and then this place is also red, and then why is the maximum actually happening at here? If this is 991, then what are the stresses on each of the separate like places holding the pins, like holding the nuts, the bolts, or the nail holding it? You can easily check and see, okay, the stress value at this place is 900 and 867, which is a lot less than this what's it called, than this. Okay, you say, okay, this is the reason why this one is actually right. Why is actually there. Now let's go to the displacement. Since we don't have time, displacement. Now now I can assure you one thing though. Now to get a different answers or a different value, you can either do two things. If you refine the meshing for this, right, you already know it's going to fail. Refining of meshing is just going to make show you how properly probably the value for this is going to tilt a little bit, like let's say instead of 91 it will be like 93 or 92 or 96, depending on how fine the meshed it is. Okay, and then but if you want to actually see real change on your value, is either you are now using a material, you now go back to what we set up. Either you're buffing up, right? Because for tomorrow we'll be working with we'll be working with real life like application, okay, for it. And you realize that you this is kind of like sort of an introduction. So tomorrow we'll be working with like, you understand? So your your all you have to do now is either you're adding reinforcement or you're adding what's it called? You're adding reinforcement, or you're changing the material and using a material that has a higher yield strength, or you are what else? Yes, meshing would do anything, or or you are reducing the force applied on it. We use 147, I think. So if you reduce your force to let's say 100, you see that the yield, the stress drops a bit. Okay, now displacement, double click and you get displacement. Displacement kind of like you do the same thing, right click, you edit definition, so you get a proper value. You select where your maximum, it's in millimeters, so you select your maximum displacement occurs, and then chart option, you kind of like use floating, so you get proper value and it's okay. So you can see that it has a maximum displacement of 2.74 millimeters. Okay, so how does it deform? What distance does it deform? From the flat plane, it deforms 2 millimeters from the top plane. Okay, so the plot kind of like tells you basically the information rate so you kind of have a view. So realistically, deformation rate, like on SolidWorks, you can easily let's see, like when I go back to stress, I can easily turn off deformation. Let's see, I used to turn off deformation. Let's You can easily turn off your deformation, select it a scale for deformation, maybe through scale, maybe you have a value per se. Deformation scale is 5.2 at the moment automatically. You can use a user defined scale and turn it to one. It wouldn't, if you turn it to one, you will see that the deformation kind of like reduces. Okay, but let's use this view and kind of like view it from this edge. Okay, so you can see kind of like there's a bit of it, like compared to when how straight it is, you see the deformation properly. This is what 2 millimeters realistically looks like. Okay, so now this whole thing kind of like now plays into um, factor of safety. Factor of safety basically tells you simply, it's not really complex. It tells you how many times that specific material would fail per use. Basically, it tells you, okay, if we have, this is a load, right? Let me just right click, factor of safety, factor of safety. Everything okay, good. It tells you that factor of safety is zero point 0.6. For every single design, your factor of safety should be at least 2. Now, reason being, what it means is that your design would have to withstand 2 times that specific load applied on it before it actually fails. That's when you know it's actually safe. But for like parts like aerodynamic parts, plane parts, specialized parts, astronauts, when you're working with robots and everything, factor of safety skyrockets to like 4 or 5 because those parts cannot fail. You understand? Under extreme circumstances, they shouldn't fail. But for things like, funny enough, for things like your car brakes, factor of safety is 2. I mean, nobody wants you to kind of, they want it to be cheap, but not so cheap, it actually fails, right? So that's kind of like the whole idea. You understand? So, Timothy, can you hear me?
Yes, sir. Yes, sir.
All right, so I have to stop here so I can,
Okay. Thank you. Thank you very much. Really appreciate your time. I think a whole lot of us got value for this lecture. So we really appreciate you. Thank you very much. For some of you that were asking some questions that, hello, can you hear me?
okay, yes, I can hear you.
Yeah. So I think you
Okay,
can go
let me
ahead.
just go. Okay, let me just go through the chat.
I think you answered most of their questions.
Okay. Yeah, I've already answered. Okay, Tabos, yeah, you can go.
Okay. You can go on. Go on.
All right, thank you again. So I just want to try something, and then I'll just say it and then Please confirm if I am correct or not. So if I want to validate my design, the stress must be less than the yield strength of the material.
Okay, okay. If I get you correctly, like you want to validate your design, and then you have a specific threshold for your stress. Like this is what you shouldn't exceed. Then, like I said, easy. You're either reinforcing. Let's say you are either depending on this on your depending on what you are doing and what you're trying to achieve. Either you're trying to achieve higher stress or lower stress. You you decide like kind of like is either you're reinforcing, either you're changing your material or you're changing the force applied on it. One of them or two of them should be constant, right? Like you cannot really, for purpose, let's say the force is a constant, right? So you now start thinking about reinforcement. Then for let's say weight or cost of production, you start thinking about okay, well, you have to kind of like now you cannot add more reinforcement because it will cost more money. You'll now start thinking about material. How about using a bigger material? So it's kind of like interchangeable. So you have to let go of which one you feel less which one you can actually let go of. Either you're working on the reinforcement or you're increasing the reducing the force applied on it. Kind of like if it was meant for 10 people to sit, you say okay, the minimum 5 people can sit on it. You've dropped it that drastically, or you can now start thinking about changing the material, maybe a much more expensive material or lighter material. So yeah, just depends on your use. Okay.
All right, noted.
All right. Thank you very much, guys. Thank you, Timothy.
Yeah, thank you everyone for joining the call. I hope we filled our attendance form. Okay, someone said I should reshare the form, so I'm going to reshare now. Please do well to fill the form. I just reshared the form now. So we go again same time tomorrow, 8 a.m., 8 p.m. to 9:30. Please do well to join the call in time. And please remember, you can see that FEA analysis, you cannot eliminate your basic mechanical, or should I say your basic engineering knowledge of factor of safety, your von Mises stress and the rest. So you cannot eliminate them when you are doing FEA analysis. They are very important. You can see that when he was trying to know the when he was trying to know if the bracket failed or not, he compared the maximum yield strength to your maximum von Mises stress, and that was how he was able to know if it failed or not. So these are the basic fundamentals that are required for you to properly understand what he taught today. So thank you everyone for joining. Okay, I think if there's no any other question, we can drop out of the call now. Thank you, everyone. Please make sure to fill your attendance before leaving. I'll be leaving the call exactly 9:20. So please fill your attendance before I leave.